Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the PLF seminar this afternoon, and my name is Rustan Leino. We're going to have two talks here today, both end of internship talks, and I have the pleasure to introduce the first of those, Clement Pitt-Claudel, who's been my intern this summer. Clement comes from MIT, where he is a grad student in Adam Chapala's group, and he's worked on taking a step forward with Dafny this summer, and he's not just worked on the project that we set out to do, but he's done an immense amount of work on other tools that he'll also tell you about. And I think just as a description of what the work could possibly achieve, there comes a point where when you work with automatic solvers like SMT solvers, that you hit some limits. And the limits can come in with quantifiers, and the question then becomes, I mean, do you stop? Is that all you can do, or can you take a step forward? And this is to the step forward.
Thanks, Rustan, and thanks everyone for coming to attend this internship. This talk, sorry. So this is going to be my end of internship talk about, generally speaking, dealing with quantifiers with new techniques and tools applied to Dafny. Just a word before I start with the core technical matter. What exactly is Dafny? Dafny is a verification-aware programming language that is a language designed with verification in mind. Like many other tools, F-star and a number of which are developed here, Dafny is based on Boogie and on Z3. Dafny runs on most common platform, has advanced editor support and a number of IDEs, in particular Emacs now. And just to give you a feel of what Dafny actually is, I'm going to give a quick demo to begin with. So I'm going to write a small program in Dafny and prove it with you. And this is running in the Emacs mode that I wrote in the context of this internship. So I'm going to write a maximum program that, given a list of integers, a sequence of integers in Dafny parlance, produces the maximum of that list. So I start by declaring the signature, and then I'm going to write the program exactly as if I was not verifying anything. So I'll write, well, I'll initialize my maximum to the first element in the sequence, and then I will loop over the sequence, declaring a variable plus starting at 0, and then looping over the sequence until we reach, well, the end of it. I look at a new element, and if the new element at that position is greater than the maximum that I've accumulated for now, then I can update my maximum to that new element. In all cases, I just increment my position variable, and that would be more or less how I would write it if I was writing it in a programming language that was not verification aware. However, Dafny is already complaining about one thing here. If I put my mouse there, it says, well, this index could be out of range. And why does it say this? Because I never guaranteed that I would only call this function with sequences that actually had an element at position 0. So I'm going to require that S be non-empty. And once I tell this to Dafny, Dafny doesn't find anything else to complain about. But notice that our maximum function doesn't actually export any guarantee yet. So I'm going to add a few guarantees, and we'll see how Dafny reacts to this. The first thing I'll say is, well, the maximum that I return is in fact a member of the sequence that I'm looking at. So when I ask Dafny to prove this, Dafny will start complaining about the while and say, I can't prove this unless, of course, I give it an invariant that, that the maximum is always in the sequence. And with that extra piece of data, Dafny manages to prove this particular entries. But that's still not the definition of a maximum. I want the maximum to be bigger than all the elements in that sequence. So I'm going to add an extra ensure that says that for all element, so for all y, or actually for all index in the sequence, if the index is in bounds, then the element at this position is smaller or equal to the maximum. And just like before, Dafny starts complaining about this. It tells me, well, this is the postcondition that might not hold here. And the reason why it doesn't hold is that Dafny doesn't have a way, Dafny doesn't actually have a way to track this thing across the loop. So I'm going to add the necessary invariance here. So I'll need 2 of these this time. And I'll just say, well, for all positions that I've already seen in my list, my maximum is, or my intermediate maximum is bigger than this. So for all I, if the element is between, well, the I is smaller than the pos, then the value there is smaller than the maximum. And now Dafny stops complaining. That's your fully verified maximum implementation in Dafny. Now, how does this actually work in terms of proving? Well, what Dafny does is it starts by converting this file, so translating this file, really, to another verification language called Boogie. So I'll actually present this differently. All right. So what it does is it produces a different file that looks like this. That's pretty long. And that says, well, so Boogie is the language to which Dafny translates. And Dafny, well, Boogie, actually, translates this down to another level, Z3, and produces a Z3 source that looks like this. So, yeah. Yeah, there's a bunch of, I mean, this is Z3 code. And then Z3 verifies this, and then we print happy messages in the editor to say, well, congratulations, you proved your maximum function. As you saw, Dafny is pretty efficient at verifying small programs. I mean, it's very fast. But larger programs actually tend to suffer a lot more. And that's due to a variety of reasons. But essentially, verification performance gets chaotic. Sometimes it's very good. Sometimes it's very bad. And it's not really clear what causes it to change. For example, you write a program that looks like this. Var y equals x, assert something. It verifies happily. But then you write var x equals y plus 0. And that fails to verify. My work here focuses on this particular issue of what we call butterfly effects. And we did it in the context of Dafny, but we expect that it can generalize to other provers. So the first question to start with here is, what causes this instability? And there are really 2 core causes for this. The first one is translation or encoding, if you will. Things that look very similar at the Dafny level may actually lead to pretty different things at the Z3 level. And Z3 will not realize the close connection that existed in the source. Another source of chaos in here is the one we focused on, is non-decidable domains. In a sense, you don't have a clear decision procedure for solving these problems. That could be nonlinear arithmetic, or it could be first-order logic. That's the one I worked on. So Z3 has a bunch of heuristics. And if the input that you give it doesn't really work well with these heuristics, you get horrible performance. And there are 2 kinds of issues here, matching loops and costly instantiations. So how do we make things better? Well, you could start by educating users. If you explain to your users what those heuristics in Z3 are and how to actually produce code that will please Z3, then maybe things will be better. Another way is to improve everything else. Maybe if there are no other problems than this, then that problem itself won't be that much of a problem anymore. And you could, of course, for the cases where things actually start going bad, improve the debugging tools so that the user at least gets a better experience when solving their problems. But what you'd really like to do is get rid of that problem, at least to the extent that it's possible. So you'd like to choose better triggers, which are what Z3 uses to guide it through its search. And you'd like to prevent those matching loops that I've already mentioned. Of course, the problem here is that if you let Z3, so if you give it very little direction, Z3 is going to search in a bunch of directions. It's going to prove a lot of things. Not very reliably, but a lot of things. If you start guiding it in a much stricter way, then there will be cases that you used to prove and that you won't be able to prove anymore. Anyhow, so what did we implement here? We implemented a bit of all that I mentioned, but our core technical contribution here is really adding a bunch of trigger-related facilities to Dafny. We now generate our own triggers, we eliminate the matching loops that we can detect, and we rewrite quantifiers in the way that we believe is going to be better for Z3. In addition to this, we created Emacs modes for Dafny, Boogie, and a bit of support for Z3. We extended the existing Axiom profiler to give better visualizations, and we added warnings in the IDEs that our users use. So let me move to the technical part of this talk. How does Dafny actually verify your program? Well, Dafny starts, it looks at your program, it parses it, type checks it, then it applies a number of transformations in the AST of your program to ensure that it ends up being more Z3 friendly, and that's really where I worked in here. Then it gets translated to Boogie, then to Z3, and finally everything gets verified. So when you send a problem to Z3 that contains quantifier, Z3 proves it in the following way. Suppose you give it, you have a fact, you know that Socrates is human, and you have a quantifier that tells you that for all element, if that element is a human, then that element is mortal. And you're trying to prove that Socrates is immortal. So Z3 has those two terms. This one is something that it knows, and this one is something that it's trying to prove, but it still has the term. And it has here an indication, an annotation on that quantifier that says, if you see something that looks like is mortal of H, then use it to instantiate this fact and learn this new fact. So Z3 says, oh, I have something that looks like Socrates is mortal. Thus, I have H is mortal for H equals Socrates. Thus, I can learn that if Socrates is human, then Socrates is mortal. But Z3, thanks to propositional reasoning, can now know that knowing that Socrates is human and knowing that Socrates being human implies him being mortal, allows it to deduce that Socrates is mortal. As you can easily imagine, choosing the wrong triggers, that is, choosing the wrong annotations on the quantifiers that you send to Z3, can cause any sort of problems, ranging from Z3 taking a very strange path to the solution and thus having unpredictable performance, or even not finding the proof at all. In general, though, Z3 is pretty good at picking triggers, as long as your formulas look as nice as what I've just shown here. But that's not actually the case in Dafny. Z3 produces extremely liberal triggers in Dafny code because of a number of issues, but mostly because Dafny produces extremely large formulas, which are written with what I call parasitic terms. They're useful in the encoding and useful to ensure that we actually make sense, but they're really not good candidates for triggering because they appear in a lot of quantifiers. Take this example. You start with S of x in Dafny. It looks simple, right? And then in Boogie, it already doesn't look that good. And when you get to the Z3 level, there is no way that Z3 would know that the interesting part was just a small bit of that thing that got expanded into a complex term. Of course, there's a number of ad hoc things that you can do to fix the situation, but what's really needed is a comprehensive approach to that problem. So how do we come up with good triggers? Well, we work at the Dafny level. That means that we look at terms that we can actually report to the user as being triggers and that we know will make sense because the user wrote them. We walk the AST. We annotate nodes that look like triggers and annotate nodes that could not be triggers. And we collect all these nodes. Then we try to find subset of all these nodes that cover all the quantified variables. We reject a number of those triggers that we found, and we eventually annotate the AST. The rejection is, of course, for performance reasons. Let me walk through an example, actually. Suppose I have for all x, p of x, and q implies p of x plus 1. I have a bunch of sub-expressions. I can exclude all the ones that mention a binary operation, because Z3 won't allow you to use these in triggers. So all of these are out. And then there just remains two good things here that I can actually choose. That means that I will annotate this quantifier with the two things, p of x and q of x. There's one nice thing here. The terms that I get are terms that literally appeared in the body of that quantifier. And so that's one of the big gains, actually. It is that when I tell the user, here are the triggers that I picked, the user can see, yeah, that makes sense. It was in my formula. I don't tell it, hey, I picked this box thing that you've never heard about before, but that I thought was a good trigger. So we don't pick the parasitic terms like box, which yields, of course, less costly instantiations. And if we don't find anything, we can actually tell the user, there's a problem with this quantifier. We can't find anything. You can let Z3 do its work, but we think that's going to yield problems. And that's not all, actually. We can start looking for a lot more things. In particular, we can start looking for matching loops, the ones I've been talking about for a while now. So what's a matching loop? Well, suppose a quantifier talks about itself in a way. That is, you give it a trigger. So you say, if you see an f of x, generate this formula. And then every time you see an f of x, you learn that f of x is smaller than f of x. Well, what happens next? You have a new term here that has an f of something. It could be f of y if y is f of x. So if you start with f of 0, you learn f of 0, at least you have this extra term, and then f of 0, and so on, and Z3 gets into a loop. And as you can imagine, too, that's not very good for your performance. The trick is that now that we have those triggers at the Dafny level, we can work on suppressing those loops. So what we can do is, for every candidate in our trigger set, we look at the body of the quantifier, and we look at the terms, and we say, this term looks like it could cause a loop with that trigger. And once we have annotated all these, we choose to exclude the ones that we think will lead to loops. And we report that information to the user, of course. But even then, that's not all, because that tends to do a lot more than you would actually want it to. take the example that I already talked about, for example. Suppose I'm trying to pick a trigger for this. Well, P of x and Q of x are two choices here. But then if I pick P, then I'll learn the term P of x plus 1 when I initiate it, and then I'm getting myself into a loop. So what do? Do I just exclude P entirely? That doesn't sound too good. Now it means that if I'll only take Q, but then now if I have P of 0, I won't be able to learn that it holds, although the quantifier tells me very clearly that for all x, P of x holds. So I've lost a lot of generality of proving power here. And one way to regain that generality, that expressivity, is to split triggers, quantifiers, sorry. So I take this quantifier and say, well, there's really two facts packaged in one quantifier here. So I can just split it in two and give two facts to Z3 for all x, P of x, and for all x, Q of x implies P of x plus 1. Now we run my usual trigger generation on this. This picks P of x here, and this picks Q of x there. And then I'm happy. Well, I'm not exactly happy, because I still am losing something. When I had this full quantifier, I had Q of x as a trigger there. If I knew Q of 0, I would gain P of 0. That's not the case anymore here. So if the user packaged those two quantifiers together because the user knew that Q of 0 would be a good term to learn P of 0, then we just lost this. How do we regain it? That's very easy. In fact, we can just share triggers between the split quantifiers. That is, we split our quantifier, but then we look for triggers, we share them between all of the quantifiers that we generated, and then we do the loop detection. That is, we look at this whole thing, we say candidates are P and Q. Now, which ones in here cause a loop? Well, none of them. So I take P and Q as the triggers for the first part of my original quantifier. And in this one, I take only Q, which is the one that doesn't yield a loop here. And that reaches an interesting situation where, in fact, the triggers that you pick for a quantifier are not necessarily inside of its body. So let me say a few words of how well that works. Well, we did two types of experiments. The first one was trying to see if it actually improved predictability. The way we measure this is we run Z3 on our we run Dafny on our full test suite 6 times with different seed parameters, with the hope that a stable test is one that doesn't stop verifying or take a lot longer when you change the seed. And what we measured then was the standard deviation of the verification time for each of those tests. And what the two plots show is the distribution of standard deviations in the case of Z3 picked triggers and in the case of Dafny picked triggers. And as you can hopefully see on these diagrams, we've significantly pushed the distribution of standard deviations with Dafny triggers towards smaller deviations. And of course, we can also look at so it was not clear to begin with that we would actually improve the performance there. I mean, we're doing more work and we're being less generic, so we could hope to gain some stability, but maybe we were going to lose performance. And actually, that's not the case. On one benchmark from the Ironclad team, Dafny generated triggers achieve a speed up of 35% over Z3 generated triggers. And there's another type of result that I actually care a lot about. What we do now is something that we can explain to the user. So we can tell the user, well, these are the triggers that we picked. And in fact, to support this point, I'm going to actually show you that we do report triggers to the user. So in this particular example, and Dafny is currently running, if I point on this particular quantifier, it will tell me two things. It split this in two, so now it has two expressions in there. Q of x implies P of x plus 1, and P of x. And it tells me, well, for that one, I picked Q of x, but I rejected P because it could loop with P of x plus 1. For the second one, however, I chose just the two triggers.
How did you do that? This yellow thing.
Popup.el.
You want it, huh?
But fortunately, it also works if you just point your mouse on it.
That's pretty cool.
And yeah, I mean, all right.
But the science is good too.
Thank you. And another thing is that even if those problems start occurring, we want the users to be able to understand better what's happening. So what we did, we came up with better visualization tools, which I'm going to demo too. The idea is that there exists an axiom profiler for Z3 already, written by Mihao, which is a great piece of software. The interface is the only thing that is slightly lacking. So what I worked on is improving that interface. So I took this example from the Dafny test suite. What I can do is ask Dafny through Boogie to profile that example. That is, for every method to measure how long it takes, which then let me pick the method that seems to be the culprit and run it through an analysis. Since this computer is not very fast, I've actually run the analysis previously. It would take a minute, but I don't want to waste a minute of anyone's time. So that's the thing that you get for one of the methods. So what the diagram shows is each node in here is a quantifier, and each edge is terms learned from that quantifier, causing other quantifiers to instantiate. So what this says is there was one thing that was apparently pretty costly, and then a number of other rather costly items that were instantiating in all directions. And this is actually with pretty strong filters, but if I showed you the entire graph, that's how it would look like, hopefully without text selection. So one thing I can do when I have this huge graph and I'm not too sure what's happening is to start filtering it. So is there a problem in the sequence with the method append on lists? Well, I just type append here, and it highlights the node that actually talk about append. So you see that there's a pretty central node here that connects to the other ones and that talk about append. So that could be an interesting direction to look at. It could also be a problem with a heap in this particular example. And in fact, yes, this example talks a lot about the heap and of related problems. So if I zoom in and I just put filters here. Actually, let me do it for real. So if I filter this a bit further, and then I relay out the graph with just these nodes, what I can see is, well, there seems to be two main culprits here. There's this thing, which is a Boogie-specific thing that I'm not interested in debugging right now, so I can just remove it. And then there's a number of other nodes, in particular this one. And now what that one says is, you have this heap-suck relation. It's transitive. And, well, it's causing a lot of instantiations of that node. And that node tells you, if you know that something is a heap-suck, then you know another fact. So what I know here is that there are problems with a heap, and that to diagnose this problem, a good thing would be to look at series of assignments to the heap that cause the successivity axiom to be used. And that thing is not only for Dafny, in fact, because I managed to sell this to the F star team, for which apparently it was at least a bit useful in having an overview of what actually happens when you run F star in a program, and reducing the shape of particular shapes that were occurring in that graph. So by means of a conclusion, one thing I'm happy about is that Dafny's next release will come with auto triggers enabled by default, entirely, or at least we hope, obviating the need for a performance hack that the Ironclad team was using up to now. We believe that the techniques that I've developed here are actually very good areas to look into. And in fact, we think that they open a whole new world of opportunities for going beyond the problems that we were seeing with verifiers and provers. And finally, what we realized is that coming up with good visualizations about these things can really yield new insight on surprising, often, verifier behaviors. And two more personal things. People at MSR were really great, so thanks a lot for having me. And Dafny and its users are pretty impressive. I'd like to thank a few people to finish. Mihao for his work on the axiom profiler. Jay for testing the Emacs mode. Alex Summers and Nick for their help with determining what this new axiom profiler would be. Brian and Chris for 3 days into my internship, allowing me to understand that this 50% performance boost that I got was essentially me replacing all the preconditions of their functions by false. And Rustan, of course, for making all of this possible and for the wonderful experience. So thank you, everyone. Yeah?
So how do you evaluate this at scale?
How do I evaluate this at scale? Do you mean on large programs? I ask Ironclad for large programs, and then I run it on those programs, and I see how long it actually takes to verify.
So what happens?
It gets 35% faster.
Overall or just one program?
Overall in the entire test suite.
On the entire test suite?
Yes.
35 is the average?
35 is, the average in the sense
what
we...
happens to the outliers and timelines?
So I've studied the Dafny test suite more precisely. So there are a few issues that are not directly connected to triggers. For example, we have things related to encodings. Those tend to have varying behaviors. Some get a bit better, some get a bit worse. In some cases, splitting your quantifier where you had an explicit loop there that had a fix me next to it will actually cause this loop to, loop more. But there's also a number of cases where, in fact, you had a loop, and so you had this instability in the test suite, and you get rid of that loop, and so you don't have the instability anymore. Mm-hmm.
So you do a lot of the things you do at the Dafny level.
Mm-hmm.
Still, I guess a lot of the theory that gets fit to Z3 just background theory and encodings of things
Mm-hmm.
that might not have direct relation to the source.
Mhm.
Do you do anything about those, or
Um,
it's just as before?
An experiment? No, we don't do anything about those things that don't come from the Dafny program. One experiment that was interested in the beginning of this internship was seeing whether reducing the amount of stuff that we told Z3 when we knew that this stuff was not going to be useful would actually help. So what I did with this experiment where essentially, it was called the Boogie Woodpecker. You would just like poke through the Dafny prelude, so the set of facts that you teach Z3 about general Dafny programs, and then try to remove as many things while keeping the program verified. And that doesn't really change performance. So Z3 is pretty good at actually discarding the stuff that it's not going to use in a proof.
What about quantifiers there? Do you have any chance of having a loop that's
The triggers
not
for
from
these.
for all you wrote, but from just
Yes, there's definitely a chance for this, and that's why the triggers in the prelude are particularly important. We've done a bit of work on them, but I mean they were written by Rustan, so they were pretty good. Other questions, maybe?
When you decide the triggers for a particular quantifier, you do it based on that quantifier alone, right? You don't look at anything in the context. Is that right?
Yeah, that's correct. We only look at the particular quantifier. There's an interesting extension of this work, which would be to say, well, we can split quantifiers now. So why don't we first package quantifiers together, then share their triggers, and then split them back? You could do this, for example, for invariants on a loop. You would imagine that they're pretty closely related. That's definitely feasible. There are tricky aspects to this with the fact that all your quantifiers might not talk about the same variables. So you need to, I mean, there are technical issues to this, but it's definitely something you could do, yes.
What about deciding whether you have matching loops that are big cycles, not like
That's also a very interesting problem, and we were hoping to do this at some point. The issue is that it's not as simple as saying this quantifier causes that one, which causes that one, which causes this one, because of multi-triggers. That is, if you have a trigger that has two terms in it, then you need to track essentially the whole history of what happened on your graph. So it's not enough to say there exists a path from here to there and then from there to here. You need to say there exists a path on essentially the product graph. You want a path on the graph of all paths on your quantifiers, and that is just huge.
So, just a quick question. So, you're doing it on Emacs. What operating systems now can you run on?
Everything that Z3 runs on actually now.
Oh, okay. So,
So-
you're using mono?
Yeah, it runs. So there were a few issues with the encodings of big integers, but we fixed those. So now we run on mono without issues. Well, the whole test suite minus one program that uses a DLL that we haven't ported yet.
Oh, sweet. Okay, so Mac OS,
Yep.
Linux.
And even FreeBSD if anyone is interested. All right.
Cool. Start.
Mhm.
So I was wondering if you know, has anybody studied the complexity of detecting a matching loop in a set of quantifiers? Is that known?
I'm not aware of work in that direction, which doesn't mean that there does not exist work in that direction.
I was just going to say, I think having more exposure at the Dafny-level is a good thing. Every time we have somebody join our team, that they start off in Dafny and they're very happy, and then inevitably they hit a problem with quantifiers, and then it's time to pull out the translation to Boogie and look at the old axiom profiler, and they get this horrified look on their face.
Oh, I didn't actually. I could have shown this.
This would be a very useful addition.
So that's the old axiom profiler. So yeah, the graph is essentially showing you this, but in a slightly different way.
Yeah, the graph is awesome. Catherine and I both used it. It's really, really useful.
So I have a question. You, at MIT, you have some hardcore experience with using talk, and talk is known for taking more time to get started with, and it's more difficult to get started with. But because it is less automatic, one could hope for more predictability. You want to compare the two?
Yeah. So I'd say it's a bit of I think it would be tricky to compare the two in that sense, because so if you look at Coq, Coq looks very manual, right? So you write your proof, and indeed everything happens exactly as you want it to happen. However, after writing 1,000 lines of trivial proof where you say reflexivity, reflexivity, commutativity, reflexivity, you get to desire some automation. Coq has a number of things that are domains where it's decidable or has like good-ish decision procedures for a number of these things. But then you get to a point where you need to write your own automation. And then what you're essentially doing is writing a small subset of Z3 that is specialized to your particular use case. The problem is that debugging this is generally as hard, if not harder, than debugging issues with Z3 itself. The thing is you end up writing your own automation, but there's no reason why writing your own automation in 10 minutes would do better than the automation that sits in Z3.
But it won't let you do unsound automation.
Actually, it will let you do anything. So it depends at what level you put the automation. If you do it in LTAC, then what you're just doing is you're calling basic tactics, which hopefully don't do unsound stuff. But you can also do it using a no-camel plugin. So the thing is that tactics in Coq, so the individual steps of reasoning, are not verified in any way. What they do is they participate in constructing a term, and then at the very end, this term is verified. So you can have a tactic that takes any goal and say that goal is solved, but then it's not going to, unless it's very smart, but otherwise it's not going to actually generate the term that does this. And so when you get to the final checking, Coq will say, this dummy proof term doesn't actually have the type that you're required to have. So yeah, I mean, Coq will let you do a lot of things with your proof term, but then at the end, you'll pay the price of not actually staying on the right path.
I think the short answer is question is yes.
OK.
All right. Anything else? So thank you very much, Leino.
Yeah, thanks again.